Hello friends, now the special purpose diode for discussion is tunnel diode. This is another important topic of diodes, and there are plenty of questions in engineering services prelims, and there can be question in gate as well, 1 mark question in gate, but there are plenty of question in engineering services prelims from this particular topic, and there is question in engineering services mains as well. So this topic is important from that point of view. A tunnel diode basically works on the phenomenon of tunneling of the charge carriers across the junction, across a forward biased junction. Remember, tunnel diode works in forward biased mode. We will see that. Fine. When P and N side of a PN junction, please try to recall the Fermi levels. When P and N layers of a PN junction diodes are heavily doped, what happens? The Fermi level on P side enters into the valence band. I repeat, when the acceptor concentration becomes greater than the density of states in the valence band. Please try to recall my video on Fermi levels. There I discussed when acceptor concentration on P side is higher, more than the density of states in valence band, the Fermi level enters into the valence band. This is valence band on P side, this is conduction band on P side, this is valence band on N side, this is conduction band on N side. When NA is greater than NV, what happens? The Fermi level is less than the highest level of valence band on P side. Similarly, when donor concentration is more than density of states in the conduction band, the Fermi level is more than the lowest level of conduction band on N side. Fine. So what I mean to say is, when donor concentration is high on P side, the Fermi level enters into the valence band at this condition. Similarly, when this is acceptor, when acceptor concentration is high, Fermi level enters into the valence band. Similarly, on N side, when donor concentration is high, it satisfies this condition, and is more than the density of states in the conduction band, the Fermi level enters into the conduction band. Fine. Such type of semiconductors are called degenerate semiconductors. We call them as degenerate semiconductors. Fine. These are the semiconductors where there is no charge carrier above the Fermi level, no electron, there is no empty energy state above the Fermi level. All the energy states are occupied below the Fermi level. All the energy states above the Fermi level are empty. I am just repeating, I am just correcting. All the energy states above the Fermi level are empty. All the energy states below the Fermi level are occupied, filled. That state of semiconductor is called a degenerate state. Fine. Now, so understand the concept here. In normal case, all the energy states below this Fermi level are occupied, all the energy states below this are occupied. Fine. Electrons are here, these are empty states. Fine. In valence band, there are empty states. Fine. In a conduction band, there are filled states. Fine. Now, I will reverse bias it. Suppose I reverse bias it. Due to reverse biasing, try to recall the Fermi levels. When a diode is reverse biased, Fermi level on P side shifts upward. Fermi level on N side shifts downward. By how much? By the level of reverse biasing voltage. So Fermi level on this side will shift upward like this. Fermi level on this side will shift downward like this. So Fermi levels will be what will happen? Fermi levels will be shifted in which case when it is reverse biased. Fine, please understand what will happen due to reverse biasing. I am taking the case of reverse bias now. When the diode is reverse biased, diode with what? Diode with heavy level of doping on P and N side is reverse biased. Fermi level on P side will shift upward, Fermi level on N side will shift downward. The gap between the two Fermi levels is Q into VR. VR is reverse biasing voltage. We have already discussed that concept in Fermi levels in semiconductors, right, and in PN junction. Now, please see this. When it is in degenerate state, see here, please understand the concept. I have field energy states, on P side, and at the same level I have empty energy states on N side. Please understand the concept. Because of this shifting of the Fermi level upward on P side, shifting of the Fermi level downward on N side, there are energy states which are occupied. Remember, in degenerate state, all the energy states below the Fermi level are occupied, all the energy states above the Fermi level are empty. So all the energy states above the Fermi level on N side are empty, all the energy states below the Fermi level on P side are filled, and because of the shifting there are empty states on this side, there are filled states on this side, but energy level is same. So what will happen? There is possibility that charge carriers may flow from this side to this side, from P side to N side. Electrons will flow from P side to N side. There are field states here in this region. Please see this. In this, if you draw this dashed line here up to this point, so in this region there are field states. So these electrons can move towards these empty states. That is called tunneling. That is known as, I will draw this line. This is known as tunneling of the charge carriers. So if you see the variation, I'll talk about the VI characteristics simultaneously. This is V, this is I. So when it is reverse bias, there is flow of the current like this because of this tunneling mechanism. So, and that varies almost linearly with voltage. Current is varying almost linearly in reverse bias mode in case of tunnel diode. So a tunnel diode behaves like a good conductor in reverse bias mode. Please do remember this. This is a question, objective type question in engineering series prelims. Now that was the case when it is reverse bias. So current will be increasing almost linearly. Now let us take another case. I'll be back again with the open circuited case. Let us talk about open circuited case. This was the case. Fine. Fermi level on both sides is at the same level. Now I will be talking about forward biased. Fine. At forward bias, when PN junction semiconductors on P and N side is forward biased, Fermi level on P side shifts downward. It is just reverse of reverse biasing. Fermi level on P side will be shifting downward. Fermi level on N side will be shifting upward. So this will shift downward, this will shift upward like this. Fine. And this will also shift, but for the time being I am taking like this. Fine. So there is shifting of the Fermi level like this. So what has happened? What is happening? All the Fermi energy states below the Fermi level on N side are occupied. All the energy states above the Fermi level are empty for degenerate state. And since there are field energy states on N side corresponding to empty energy states on P side, there will be flow of the electrons from this side to this side. When electrons flow from this side to this side, holes flow from this side to this side, that is forward bias current, and this is known as tunneling. tunneling happens because of empty energy states on one side corresponding to field energy states on the another side of the junction. That phenomena is known as tunneling. So current will be increasing linearly on this side as well. Fine, clear? Now let us see the case now. You increase the forward bias. You increase the forward bias, there will be a stage. There will be a stage. Which stage? When the Fermi level on N side will coincide with EVP, that is for the highest valence band on P side, highest energy level of valence band on P side, and Fermi level on P side will correspond to what? Lowest energy level of valence band. So there will be, in that case, there will be maximum number of occupied energy states corresponding to maximum number of empty energy states on P side. This will be maximum condition of maximum energy states occupied on N side, condition of maximum energy states field vacant on P side. So tunneling current will be maximum, and that state, that current is known as peak current. You will understand when I talk about it gradually. Fine. So Fermi level on this side is shifting downward, Fermi level on that side is shifting upward. N side shifts upward, P side shifts downward. So let us see the case now. Now what will happen? You increase the voltage again, the Fermi level is shifting, and remember, lowest energy level of the conduction band, both will be shifting. It is not only Fermi level. So when both are shifting upward, so what will happen here? You please see, there will be now the case, this is ECN, this is EFN. Again, because of the shifting upward, now these are the energy states which are filled, these are empty energy states. Now, but this area, the number of energy states which are full occupied are less as compared to this side. So this will be tunneling, but now current starts decreasing. Why? Because in earlier case, it was the maximum overlap of occupied energy states with maximum number of empty energy states, though both will be overlapping. But now because of shifting, the field energy states and empty energy states are comparatively less as compared to this point. Fine, this current starts decreasing now, and there will be a state, a condition will be reached when this lowest level of conduction band on N side and Fermi level on N side, both will be shifted upward, and there will not be any, yes, there will not be any overlapping between the field energy states on this side and empty energy states on this side. So that will be the state when current will be at minimum level. That is the condition when your highest level of the valence band is corresponding to the lowest level of conduction band. There are no overlapping at all, and then current becomes at minimum level, and that is known as IV. This is peak, and this is called valley. That is called valley point. Fine. Voltage corresponding to this is called V. Voltage corresponding to this is known as peak voltage, and after this, the lowest level of conduction band is above the highest level of valence band on P side. This is the case of a normal PN junction diode. So here current starts increasing. Current increases because of the diffusion of the carriers from P side to N side. So this current, the diode behaves like normal diode. This is normal diode, and this is normal diode, and it is nothing but diffusion current, diffusion of the carriers from P side to N side, and this is called negative resistance region. Fine. So from here to up to this point, which is this current? This is tunneling current. So tunneling current is right from reverse biasing up to the valley voltage, up to this valley point. This is tunneling. After valley point, it is purely diffusion, just like a general purpose diode. I have explained you the VI characteristic as well. Specifically, I had not mentioned that, but we have discussed the VI characteristic of tunnel diode. Fine. Okay, so this is called negative resistance region, and remember, a tunnel diode is always operated in negative resistance region of forward biased mode. So I repeat, tunnel diode is operated in first quadrant and in negative resistance region of VI characteristic. So if you see, for a particular current in forward bias mode, there are three voltages corresponding to the same current: Vp, V1, V2, V3. So I mean to say, for the same current I have the three different voltages, because of which it is suitable for pulse and digital circuits. Fine. So tunnel diode is suitable for pulse and digital circuits. And this voltage from 0 to VV, it is small voltage, less than 0.7 or 0.6. It's not high voltage, very small voltage. Fine. Another point, since it has a negative resistance, and all the devices which exhibit resistance, negative resistance, these are suitable for microwave frequencies. Any device, any semiconductor device which exhibits negative resistance in its characteristic, that is suitable for microwave frequency operations. So it can be used as a microwave frequency switch. There are many applications. So a tunnel diode is suitable for microwave frequencies. That is another question, objective type question. This characteristic itself can be one question. This negative resistance region can be the question. Valley and peak points, that concept I have already explained. So these are some of the questions as far as exam is concerned. There can be many questions, theoretical questions on this. What is the symbol? Symbol of this? Symbol of tunnel diode is simple symbol like this. That is the symbol of tunnel diode. So I hope the concept of this is clear. And if you talk about doping, in case of general purpose diode, doping level, there can be a question on doping level in engineering services prelims. In case of general purpose diode, the impurity is what? Impurity is 1 atom per 10 raised to power 8 atoms of semiconductors. That is the doping level. Fine. In case of tunnel diode, it is 1 atom. It is 1 atom. 1 atom per 10 raised to power 3. It is 10 raised to power 8. It is per 10 raised to power 3 atoms of semiconductor. So that is the level of doping, approximate level of doping in tunnel diode. These are small question in engineering services prelims. They have question on even on data. So this can be the question, the level of doping in tunnel diode. So that is the level of doping. There can be question on this level of doping in general purpose diode of order of 1 atom per 10 raised to power 8 atoms. Fine. So this is your the doping level in case of tunnel diode. Now we have discussed the energy bias diagram, we have discussed about the symbol, we have discussed about the VI characteristic. So let us talk about equivalent circuit of tunnel diode. Of tunnel diode is nothing but a resistance, an inductance, then we have a capacitance of the junction and a negative resistance. So this is minus R. This is contact resistance, this is inductance of the leads, resistance of the leads, inductance of the leads, capacitance of the junction, and this is the negative resistance exhibited by the device. So that is your equivalent circuit of the tunnel diode. Fine. Now let us talk about the applications. What are the applications? Tunnel diode can be used as a very high frequency switch, microwave frequency switch. That is what I discussed. It can be used as a microwave frequency oscillator, and third, it can be used in pulse and digital circuits. These are some of the applications. Fine. What are the materials used? Materials used, this is question in exam, engineering services prelims of course. The materials used are germanium and gallium arsenide. Note, silicon is not suitable. Why? Because of, it is because of what? Because of low peak to valley current ratio. So silicon is not used for fabrication of tunnel diode. It is germanium and gallium arsenide which are used for fabrication of tunnel diode. Fine. So these are some of the important points of tunnel diode. There can be questions in IES prelims, many questions in IES prelims. So please do remember whatever I said. Fine. So wait for my next video. I'll be talking about another important diode which is important from GATE examination point of view as well, and there are questions in engineering services also, that is photodiode, and then we will talk about the solar cell. So there are a lot of questions from these two topics in GATE. So just wait for the next video. Thank you for watching.